Hi everyone. Am I audible? Okay. In this tutorial, I'm going to be talking about martial arts meets machine learning, recognizing judo throws with MMAction2. So, my name is Habeeb Shopeju. Currently working as a research engineer, machine learning at the Thomson Reuters Labs. My main interests are building information retrieval systems and machine learning systems from Lagos, Nigeria. I kind of started working on this project sometime last year. It's basically a personal project, and it did turn out to be something interesting to work on, from getting to source for data sets and finding the right tools and just getting something that works, considering the fact that it's like data sets do not exist for this particular task. For the MMAction2 library or framework, I found that to be quite useful as well. So while you may not be very interested in Judo, the same concepts can be taken using the library and using the same knowledge into other kind of action recognition tasks. So, to get started, a Judo primer. This is going to be like quite short because I'm just going to walk you through what the sport is about, so you get to understand what the throws are, what keywords are, and maybe that could make it much more fun. So, just a breakdown of what I'm going to be talking about next, the gentle way, glossary, some throw examples, and what exactly makes a throw work. So Judo was created in 1882 rather, by Jigoro Kano, and it's been an Olympic sport since 1964. So it's a sport that kind of builds on the maximum efficient use of energy. So it's not about using force to move your opponent. It's about understanding how the body works and using their own energy against them. And while doing this, you need to keep them safe. So it's not just causing harm, it's disarming them without making them like get injured or anything of that sort. Judo has also influenced other martial arts. For example, Russian Sambo and Brazilian Jiu-Jitsu. So both sports are like quite similar, except Judo, in comparison to Jiu-Jitsu, is much more standing. So you like stand a lot more compared to Jiu-Jitsu, where you go to the ground more. So just a brief history. So Ansakomake, that's basically, think of it if you watch soccer or football, where you get like a red card. So Ansakomake is like something of that sort, where it's an accumulation of smaller fouls, or like just something you get when you do something like very dangerous. And Ippon is a classic victory. So the idea of an Ippon is you take your opponent and then you put their back to the ground with impetus, so like with force and with control. So those two things are quite important because like you need to show that you did throw them, and then you need to keep control of your opponent so you don't injure them at the same time. The judo gi is the judo uniform, which is what I was wearing in the previous slide. The judoka is someone who does judo. Waza is just a generic term for judo techniques. So ashiwaza, which is like a foot technique for your sweeps. Tewaza, your hand technique, so you use your hands. Koshiwaza, where you use your hips. Waza-ari, in comparison to the Ippon, is a smaller score. So say you throw your opponent, but it's not with as much control as it would be in an Ippon, or you don't hold them down for long enough. Just second slide here. So Randori basically is what is referred to as a free sparring drill. Shido is a light penalty, so you accumulate shidos to get an ansakomake. So a shido could be thought of as a yellow card in this case. Uchikomi is just the repeated practice of a throw up to the point where you want to execute, but you don't execute it So the whole idea is you build muscle memory by repeating certain actions, say a lot of times, such that while you are competing, you don't like get to think about your throws, you just do them. I think that could be similar to how you see how we type a lot these days. Like when you first started typing, you'd probably be looking at your keyboards and looking for where the keys are. But now, because you've done it multiple times, you just know where the keys are. The uke is the player receiving the opponent's attack, while ukemi is a group of break fall techniques. So it's not just about the throws, it's also about the falls. So to do judo, you need to learn how to fall so you can protect yourself while falling. That's like something that makes it also much more beneficial, because now you don't just fall without putting the right techniques in place, while the tori is the player executing the attack. So this is examples of some throws. The one to the left is the uchimata, where you see the tori uses his hands and then uses the legs as well. While by the one to the right is an osotogari, where the tori also uses her hands and then her legs. Basically, the idea is, if you look at both of them, they both get their opponents onto their backs with force while keeping the control intact. So, step-step approach to a throw, kumikata, which is your grip. So you need to have your grip right, always. Without the grip, you really can't throw properly. So that needs to be right. Then off balancing, which is kuzushi. You really can't throw someone who is like in a very fixed position. So you need to off balance them, get them out of their balanced state first for your throw to work. It's like creating momentum for your throw. Then setting up the throw, sukuri, which is like you're going into your throw this time around after you off balance your opponent, and kake, execution. So just one more slide to show you those examples. If you look at the sio nagi, you see the tori kind of hits the opponent and then gets him to move forward, which is like kuzushi, and then just goes right under, like it disappears in quick time, 2 seconds, 1 second, it gets it done. While the other one is the tomoe nagi. While that's much more demonstrative rather than in action, the idea is he creates kuzushi, like pulling the opponent forward, and then goes into the throw by going down and executing the throw while keeping the hands intact. Sorry about that. That's enough of judo for now. So, action recognition. So, I'm going to be talking about object detection, which I think is a bit much more common and much more popular. Then the use of object detection for action recognition. Then action recognition on its own, and the models that are quite popular in action recognition. So for object detection, it's a computer vision task for detecting objects. I think the name kind of sounds explanatory. So you have a picture, you have objects. In that picture, you can tell what objects are in it. So for example, here you have like a dog and a cat in the same picture, and you can tell just through an object detection model. Some popular models for these include the Judo, Faster CNN, and RetinaNet. So those models are all built on convolutional neural networks, and then you just build off of that same base for object detection. So using object detection for action recognition, this is like a common task, being able to tell from sign languages what's been said. So for example, in the left, you can tell that's saying yeah now, right? And then it's saying rock, Spider-Man, rock, Spider-Man. And you can tell from a video using an object detection model. The way you can do this is because a video is just a collection of images. So you can take a single frame, run that through your object detection model, and be able to tell that, oh, this sign language means this. then you kind of combine multiple frames when the meaning changes and be able to tell what exactly is going on just using a naive approach of an object detection model. For example, at the right, you can see that's a fist, just a single frame, and you can tell that that's a fist just from a single frame. Okay? So now, can you tell if this door is being opened or being closed? If you think it's been opened, can you raise your hand? If you think it's been closed, can you raise your hand? Okay. The door has been closed. So the whole point here is, while in the previous case we could tell the action based on just a single frame, for much more complicated scenarios, you need the whole picture from the start to the finish to know what exactly is going on, to tell what action is being executed in that video. So basically, action recognition is the computer vision task of recognizing human actions in images or videos, then categorizing them into classes. So it's object detection, but with a little bit much more complexity. So what are the challenges here? The temporal dynamics. So by temporal dynamics, this just means you can't just rely on a single frame now. You need to rely on, like, you need the first second to know, you need the first second and then the third second, maybe the second to know what is being done in that video. And then there's like a variety in spatial appearance. So there are multiple ways to perform a certain action. So if it's to open a door, for example, there are like a multitude of ways to open the door. So it's a lot of complexity for the features you'd be extracting from a video compared to an image where it's just a single frame. And this is not even talking about the temporal parts here. It's just complex in nature. Then the context dependency. So there are different actions that share the same attributes. So for example, the picture I showed where it looked like the person was either opening or closing the door, that's just one frame. And there's like context dependency of that action across multiple kind of actions. So that also makes it challenging to work on. Some popular models for this are the C3D, X3D, CSN transformer. I'm just going to talk a little bit about some of them and their main ideas. So for the C3D, it's from a paper, Learning Spatiotemporal Features with 3D convolutional networks. So the main idea here is you are using convolution as you would do in an image if you are working with object detection. But the difference is there is one more dimension. So it's not just the height and the width, now there's the time dimension. So that's what makes it 3D. And then they're also doing pooling. So that's, for previous approaches, you would probably have just used 2D convolution. So you do 2D convolution on multiple frames, and then you try to do some aggregation on those, but it does not just work well enough. Then they try to do spatiotemporal feature learning. Basically what this means is, if you have, as you would do with an image, with object detection, you're trying to learn features across time here, and that's one of the key ideas from their paper as well. Then the whole idea is finally to put together your 3D convolutional network, pull in a fully connected layer and your linear classifier. If it were to be an object detection task, then just using your 2D convolutional neural network, or your 2D layers rather, your pooling and your fully connected layer would work fine. Now this would be done on say a video has like 45 frames per second, for example. In this case, they got their models to work fine, say for 16 frames. So like 16 frames may not possibly even get to 1 second or 2 seconds, but it's a step in the right direction. That's 2014, by the way. Then 2016, this is the temporal segment networks for action recognition in videos. This is also one of the models that is going to be used in my notebook, because there are like 2 notebooks in this tutorial, and we are going to be walking through those. So the idea here is, across a video, you would have a lot of redundancy. So say a video could have, say a video could have 1,000 frames. You could easily assume that 50 of those frames would be redundant per segment. So if speaking now, and that's like 50 frames, like my hands are still in the same position, so it's efficient enough to just take a sample per segment, and then they make use of an aggregation function to find an aggregate of the features gotten per segment and make their classification on that video. Now this works, and then it helps with like long-range temporal structure, because it now works on much longer videos. By much longer videos, I don't mean it's even up to a minute. It's like just very short videos, but it still does the job. Then this is much more recent, from 2021. Is space-time attention all you need for video understanding? And the key idea here is they made use of a transformer architecture, and this is unlike previous models. This is unlike previous models, which used the 3D convolutional layers. Now they make use of the whole attention-based mechanism on the videos. The main way they went about doing this is to create patches. So just to explain what a patch is, say you have a video, and then it's like 36 by 36. They create patches on a single frame. So say you divide a frame into multiple boxes. Say 36 by 36, say you have now six boxes horizontally and vertically. So like just create multiple boxes in those, and you try to make those patches or boxes into embeddings of their own. If you've worked with text before, then this probably easily makes sense for converting tokens into embeddings. So it's the same or similar concept with using the patches here. Now, the other key idea they have is divided attention. So in this case, they are not just putting together this, trying to find spaced attention within the patches. They're also doing this both temporal, in the temporal space and in the spatial space. So if you have, say, a patch at the top left, they try to find the attention across multiple frames, and they also do that spatially as well. So say you have your 36 by 36 frame, you try to find the attention of the top left patch with, say, the bottom right patch or other patches. So the idea is they do divided attention, and they combine those for action recognition purposes. So now going into the main library used for this project, which is the MMAction2. So just going to talk about the Open MM Lab ecosystem config fundamentals, because it's mainly working with configs, except you're intending to modify existing models, data pipeline, the data loader model, other APIs, then how training and inference works. So this is just a screenshot, and what I'm hoping to point out here is it's not just the MMAction2 library. They also have other libraries in the ecosystem. So the MM engine, for example, or the MM detection, MM segmentation, MM OCR, which you could use for text detection, MM pose for pose estimation toolbox, MMAction2, which is being used in this tutorial, And then they have something called MIM, MIM, which is what you'd use to install their other packages when you're performing whatever task it is you want to perform. So I'm just going to walk through some of the fundamentals here. Now I'm hoping you can see this, but this is like a config fundamental. So let's say this is like a random config.py file. The idea here is you can put together the various bits that you would use to train your model, and you do this with like a key value pair structure. So for example, the first part in bold, which is dataset type, video dataset, it's kind of stating what kind of dataset you are passing in, because there are various datasets you could use. Say a raw action dataset, which is not just your video, but your video in the RGB flow state. But video dataset in this case just works. Then you have your train pipeline, where I'm pointing across to the resize, which is just one part of the pipeline, which is resizing the video after you read it in. Then you have your train data loader as well. In that case, it's just taking use of the data sets, and that's the variable that determines how you get to load your videos in. So you can see it as like the batch size, the number of workers that will be passing your images, or your videos rather, to your GPUs. But the main idea here is the configs work with like key value pairs. So it's just you figure out what variable you need to change to affect something in the pipeline, and then you change it, or you add your own custom classes or functions, however it may be, to work for you. So it also uses like the dot notation. So in this case, I'm reading in the random config file. So just doing like an engine config, reading the file, and you can access, using the dot notation, you can access the variables. This way you could easily modify something else in a new config file. And then from the list as well, you can see the indexing works, as well as the dot notation combined. So it's basically making use of your key value pairs and being able to access your config files with dot notation. Then something else that's also quite important from the config is the modular inheritance design. So at the top you have, say, small random config pi, which has like a base variable there. What this does is it inherits the config from the random config pi file. So let me just go back to that so you remember that. So this config pi file is what is being inherited here, and it inherits it using that base variable. For the dataset type, now it's going to be changed. So it takes all the variables you've defined from the random config.py file, and then whenever it is you define them here, it just modifies those variables, if that makes any sense, to use for your use case. Then for the train pipeline, I'm basically just changing the scale there, where scale refers to this one, which is in bold here. So that was 224, and it's been changed to like 448. And in the Python IDE, I'm just like checking, so you see that's actually been changed in the small random config file. So just to come over again, the key value pairs, your dot notation, which you would use to access variables, and then the modular and inheritance design, which makes it possible to make use of existing configs without having to like copy paste or rewrite the whole thing for your use case. Okay, so going into what the data pipeline looks like, this is the train pipeline. It can be changed into like the validation pipeline. So in this case, you have the decode in it, which is just the class that's being used to read the videos in. Then your uniform sample what uniform sample does in this case is it takes your video in, and then as I mentioned earlier, you can't just like read in all the frames. You need to like sample appropriately. So like a clip length of 8 per sample, and what number of clips just means is how many samples it takes from your video. Because the code is basically just making those into the proper format for the rest of the classes in your pipeline to use. So like your resize, the PyTouch video wrapper, your random resize crop. Then at the bottom, that's like the format shape and the pack action inputs. Those are needed for like other parts of the MMAction library. It basically just consists of like say a dictionary that has your features and other metadata needed. So you have other data pipeline APIs. So it's not just the decode in it. You could also use like OpenCV for reading your videos in if you have any reason to want to do that. Then your sampling, there are other types of sampling APIs you could use as needed. Augmentation, so you could do like center cropping, which is like just cropping the center part of the video, flipping, say horizontally or vertically as need be. The PyTouch video wrapper and IMG.org. I'm quite interested in IMG.org because it's kind of a different library that's being used for image augmentation. So it allows you to make use of an external library like that in your data pipeline. So others, there are like a lot of other APIs, which includes like format shape, which I talked about earlier, pack action puts, normalized 2D, and transpose. There's like a page which talks about those APIs. So if you're interested in them, you could just take a look at those. Looking at the train data loader, I talked about this a bit earlier. So you have the batch size, where the batch size says how much videos you want to load in. If you are using a GPU that does not have lots of memory, then you would not be using a huge batch size. So something of 4, 8 would probably suffice. Number of workers depends, it's on the CPU end. It's basically just influences how many workers would be used to load your images into the GPUs. While the dataset type was a variable defined earlier, the ANN file train, that refers to a text file, which we are going to be looking at soon. A text file that contains the file name and the class for that action being performed in that file. Your data prefix, which could be like your train folder or your test folder, while the train pipeline is the train pipeline defined from earlier, which is this one. Since it's the data loader, it needs the train pipeline to perform actions on your videos before it loads it into the training process. Then this other one, which I think is quite important, the model config. In this case, this is extracted from the TSN model, and the important part is the class head, which in this case is like the TSN head, but you can see number of classes. So for number of classes, you can decide to change how many actions or how many classes it is you have in your data set. So if you intend to create an action recognition model for like 5 classes, you just change that to 5 and it will figure it out. While the RESTnet type is the backbone type. If you have some experience with object detection models, then you probably know what the backbone means. So the backbone is basically the model that exists, which you use for feature extraction purposes, and you'd likely build your new model on top of that. So other APIs for your model, so like the RESTnet for your backbone, you can use the Uniformer X3D Vision Transformer. Once again, this all comes down to knowing what exactly it is you want to achieve for your action recognition model. While your data preprocessors, these are, say you want to like normalize your images in your video, these APIs give you the ability to do that. Then for your heads, the base head, TSN head, there's a variety of those, and you can also configure your losses for your training process. Other APIs that I think would be useful, or at least they're useful for me, the accuracy metric you could use. You could change how many classes it is you want to find the accuracy for. So if it's for the top 3 classes, for the top 5 classes, as need may be, the confusion matrix can be calculated, can be implemented rather. For your hooks, you have the checkpoint hook, visualization hook, logger hook. What the checkpoint hook influences is how often you get to checkpoint your model while training. So do you want to checkpoint your models per epoch, or every 2 epochs, and so on and so forth, while the logger hook determines how often you get to log the training process. There are various optimizers. If you use PyTorch a lot, then it supports all of PyTorch's optimizers in this case. Then it has support for most of PyTorch schedulers as well. So for training and inference, it could be as simple as just calling your train.py file and your config file, and it just trains it. While for your inference, you load in your config file, the checkpoint file, say you finish training the model, it gets saved into a checkpoint. It gets saved as a checkpoint, then you load that in. Then you load in your video file into the recognizer, and you make your inference. So that's about it for that part. We're going to be working on the notebook now. Just going to open this up, and this is going to be working on datasets, kinetics, 400 tiny. This is from the kinetics 400 dataset, which they just created. I think the MMAction team created this, just 40 clips, which consists of just 2 classes. What kinetics 400 dataset is it contains 400 different action types. And there's also kinetics 700 for 700 action data types. So that's the collab URL. So you could just open it up. That would be great. So we could just walk through those. For the link again, I'll just leave it there for a minute, just so you can get that in. Quickly, data I need PyData. It's going to be opening a collab notebook, which contains like the instructions for this data set. Okay. Alright. Now that it's opened up, just going to be connecting this. This is the initial setup for the MMAction2 library. So just keep installing the necessities, the MM engine, which I talked about earlier, the MMCD, and then the MMAction2 library itself. So that just goes. Let's see one more time. Okay. So it's basically just installing this. If there's anyone who is here to get the link or is open to get the link, I could just put it back there for other ones. While we wait, are there any questions so far in regards to the library or action recognition models? Okay.
Sorry, is this code available on the information? Can we access it?
Yes, you can access it. It's if you just visit the URL, you'll be able to find the collab. I don't know if this changes it. Where is it? Yeah, this URL.
Access is Was the transformer-based approach, how that performed compared to the other convolutions and things that were out at the time?
Way better. I can't give the exact numbers, but way better. Because it's using the attention-based mechanism as well, not just using like a 3D convolutional layer, so it's like way better. I was actually thinking it would overfit on like everything, since it's, first because it's not a large data set I'm using, so there's that tendency. But even from the metrics and the research work published, it's like, it beats them, basically, so.
Thanks.
Yeah, so based on your research, is the transformers approach the state-of-the-art, so there's one in time for action recognition?
Yes, that's the state of the art. It's not just like transformers itself, it's variations of it. So, for example, there could be like MVIT, for example, which also builds on transformers. So everything I've seen so far from the state of the art models all build on transformers in one way or the other. So basically, everybody has moved on from 3D convolutional layers at this point. So that's done installing. So this here would download the config file for the TSN model, where TSN is the temporal segmented network I talked about earlier. So just gets to download that. And for JSON, so here I'm just downloading the kinetics tiny dataset. And unzipping it, so you find here, let me just take this out. You find here it has the downloaded config file for TSN, and then it also has the weights for TSN as well. Where the kinetics 400 dataset looks like this. Looking into the tiny bar video, this is the format which I talked about earlier for the ANN file type. So your file name and the class type. So what I'm doing here is I'm trying to create just a text file that contains the name of the class, basically. It's going to be used for inference. Just do that. I hope I've not run that before, but let's see. This is just a function to play videos in Colab. Next would be creating the config file, so just an empty config file, and yeah, that should appear here. So here it is, custom config, and that's what we're going to be working with next. So just going to be walking through each of these as I move them to the custom config.py file. So this is the base variable I talked about earlier, which you'd use to inherit configs. So just move that in, just copy paste everything, but hoping to provide explanations for each line so you understand what's going on. So that file is coming from the downloaded config file from earlier, if you recollect, which is here, the TSN ImageNet split range. Okay. Then I'm setting the data paths. So you have your data roots, data var, your ANN file train, your ANN file var, and ANN file test. In this case, I'm just using the same validation file for the tests scenario, not like it's going to be used anyway, just to ensure the right file paths are set. So just going to move that in. Next would be the data loaders. So the parts that I'm changing from the initial config are the batch size and the number of workers, as well as the ANN file path and data prefix. To provide more context, I think it's going to be good to open the other file side by side so you see what changes would be affected. If we go towards the train data loader, so you can see here, I think that's been modified already. Yeah, so you have in the original config file, the sets to make use of the kinetics 400 datasets, which is not what we are using. We are changing datasets type, which is what we are setting at this point here for the NN file and data prefix. And we do that for all the data loaders. So let's just move that in. Just feels like copy and paste, but it will take some time to figure out the right things if we are doing this in real time, because I had already worked on this notebook previously. That's why it just feels like it's copy and paste. Then for the model, I'm making a change to the number of classes. So here, I'm just going to show you where the number of classes exist in the actual file, in the actual config file, so you can see. You can see number of classes for the TSN end is 400 here, so just changing that. If you have any reason to want to change anything else, it's the same pattern. You find what variables need to be changed, you find what exactly they mean, and you fix those to fit your use case. Then for this, I'm modifying the train config to just use maximum epochs of 10. So we could also check to see what that will change. In the train config, here. Oops. And then load from. What load from changes is the base image, the base weights you intend to use. So in this case, we are making use of the TSN ImageNet pre-trained base weights as well. Yeah.
I have a question, which is, so just before like this cell you're in right now,
yes,
where you essentially, just before this, you created the config, the custom config, right? So how come yours seems to be populated, but when I look at mine, it's empty? Right.
Yeah, it wasn't populated, it was empty as well. Like I'm just moving stuff into it.
Oh, okay.
So the one that's populated is the existing config file, which was downloaded previously. So that's what's populated. I'm basically just making a comparison between the changes you are making, and then so you can also see what the actual configuration was previously. So what else? Then the checkpoint hook. This is probably not necessary, but I just thought to put that in for educational purposes, I guess. So this modifies the checkpoints as well. If it feels like you really don't know what variables are affecting what, there's like a file, a page on their documentation that kind of talks about what the variables mean and what classes affects the various parts of the training pipeline. So now that that's done, let's save. Okay. Then to train a model. So there's something I think I should mention. Let's close this tab. There are about 2 ways to install the MMAction library. So you either just install like with pip, or you build it yourself. So according to them, when you build yourself, you probably go through that route if you intend to like modify an existing model, if you intend to change something in their APIs. But if you only need to like call them and perform inference, then just doing pip install would work, which is exactly what I did here. And then to train the model, I'm making use of the main config, the main package rather, not config. Then training the model on the custom config file. So because it's a very small data set, it's not going to take a long time to train. But you can just see what the training process looks like. It logs all of this. Okay. If you're a demo.
Sir,
Yeah.
maybe you have a custom
Yeah.
from line 3 to 8. You have, it seems like you have like a duplication. Is that intentional?
Line
3 to
3
8.
to 8.
Scroll up, like line 10 to 15.
Okay, no, it's not intentional. It's like I copied those multiple times. Thank you. I think I could just copy paste the whole thing. Since I've explained it. So there's like this error message here that talks about a mismatch from 400 to like, based on the shape, from 400 to 408, which is the size of the embeddings being used, to 2048. So that's normal, mainly because the model, the weights we are loading in come with like the 400 by 2048 dimension size, and we're just changing that in. So this should be done training soon. So yeah, that's it. Training finished successfully. So for loading the model in, you have the init recognizer and the inference recognizer as well. I hope it's visible.
Yeah, if you can zoom in a little bit, that would be great.
Okay. Yeah, just occurred to me that it could be like very small. That's too much. Okay, so here, what this points towards is the output directory, which is here. So it saves it in this work deals folder, and then custom config, custom underscore config. And I'm just picking it up from here. So you could change where you intend to have your output file saved. So if you don't intend to have it saved locally, it's actually also possible to fix it anywhere else based on the configuration. And then it has saves the best epochs, the best weights, more like. Yeah. So I'm just making use of the config file and the best weights from checkpoints in. So passing those in, and then the label tiny.txt is the one I created earlier using the echo and redirection, which is here. Basically just a random class, because I really do not know what classes are in the videos for the dataset they created. So let's just do this to load the model. Then finally you can now predict, this is not a flow basically, but it's on their own data sets. So the influence recognizer, get the results, and whatever processing is needed. I think I don't need to walk through that code since it's kind of basic, I guess. Then you print out the labels and corresponding scores for the classes. So now this is just 2 classes. I have to play the video so we see what exactly is in the video. So this is the contents of that video, and it says class B. I don't know what action is being performed here. Does anyone know? I have zero idea what it works. So now that that's done, and I hope it's like passes across the fundamentals of how the library works and how you can put things together to train your custom model. Now you're going to be doing this yourself on the actual data set I created. So I made up the data sets from YouTube videos, extracting the right time frames for each throw, and 7 classes, just about 500 clips. And the collab notebook is here. So I would appreciate if people could run this themselves and you could just walk through that. If anyone would like to do that, this is the link. You just open that up. So it's basically the same process, except now I decided to change a few more things. I'm just going to talk about some of those things I decided to change. Just leave the link here for a while.
Excuse me, can I ask a question?
Okay.
So self-curating a data set, it sounds like extremely laborious. How long did it take you? What did you use? How did you do it?
Well, yes, it's extremely laborious, but it took a while because I was like just interested in getting it done. Like,
sure.
There's a challenge of getting someone to explain what a throw means to someone and getting them to know what they should look for. So I just felt to just do that to myself, like follow videos, and yeah, quite manual. I had like this basic Streamlit tool where I was just putting like a YouTube video link in it and just typing in the timestamps and just extracting them and pushing them to like an object store or something. So it's same process as earlier if anyone wants to go to the link. So a couple of things that changed here is it's going to take a longer time for this to train. I think about 15 minutes. So I think it's just going to be good to run it and explain the changes while that runs. If you intend to like follow through, that would be awesome. So here, installing this, same thing. Gdown. So Gdown basically is what I use to download this set from a Google Drive because I uploaded it to a Google Drive. So I'm just downloading it from there. Okay, so where's that later going on? Still installing. Done. Does anyone have any challenges with the notebooks? If anyone is doing that. Any challenges?
Yeah, it's still installing libraries.
Yeah, mine's encountered an error on the second box inside the config file subheading.
Okay, can I come take a look?
There's something that thinks there's a list, but it's not a list. Yeah, we got an error saying trying to access train pipeline or list of functions in the base.
Okay, so
basically,
yeah, so I think you need to copy this into the custom copy file.
I see.
certification encountered was from here. So this cell here, you don't necessarily need to run it. You just need to copy it into your custom config file, since it's going to be running from the config file anyway. And it works if you run this cell. So downloading the config file for the times format. So this is different from the TSN, which was used on the previous notebook. So this is way better. This is just a custom function I worked on to split the data sets. Downloading data sets from Drive. Basically just creating the necessary formats needed. To explain the format again. So you have your root directory or root folder. You have your plain folder. In that root folder, you have your validation folder as well. And then your ANN files for your plain or your test. So you should modify all of this into the right places. If I refresh, it should be done. Yeah, so it gets that done. Then this displays the video. Then we touch custom config. Okay, so just going to copy paste this in. That's the model in. Yep.
With this action, can you change like the runtime to GPU and it'll be faster, or?
I'm using the GPU actually.
Okay.
So if you interact with the GPU in your collab, I think you could do that from like runtime.
Yeah.
So change runtime. I don't know what interface it will show for you, but this is what I get when I use collab. So you don't need to use a CPU because that'll take ages. So just going to copy this in. Okay, continue to touch the cartoon. Instead, then turning the model so I can come back to explain what the changes imply. Okay, I think it's going to start turning now. Also close this. Yeah. Do I have to close it? Okay. We need to just compare this one first. With the times format space only. So the model I'm using here is the times format space only model. There are different times format models. So from the slides earlier, I talked about the idea of the times format being doing attention mechanism on the spatial parts of the video as well as the temporal parts. So this is just neglecting, not necessarily neglecting completely, but focusing more on the attention mechanism for the spatial aspects of the video. I think one of the reasons it probably worked is because the videos are like quite small. For a judo throw, it probably takes like 1 or 2 seconds to complete it, so you really would not have 10-second long videos. So just like 2-3 seconds would suffice. So to just compare this, from the beginning, the same base, inheriting from the config file, downloaded earlier, setting the data paths, where the data paths were put in place by the custom function I ran earlier, which downloads the data sets and puts the right files in the right places. So if you have to be working on your own use case, then you probably have to figure out how to put those in place as well, based on your data sets. So this for batch size of 4, number of workers 2. Number of workers 2 because on Collab, I think it's just like 2 workers you can get based on the compute they provide. The number of classes 7, which is because I have only 7 classes. So while Judo has like 68 flows, like if there's a big enough data set for that, then this will probably be 68. Or if you have like a use case where it's just 5 actions you're hoping to recognize, you just use 5 for that. Then the epoch-based train loop for the train config, setting that to max epochs of 10. I think it does fine even at 8 epochs, to be honest. No, does fine is an understatement, does well. Then for the checkpoints, checkpointing every 2 intervals, then keeping max checkpoints of 3. So if it exceeds 3, it deletes the weaker ones. Then loading from the weights downloaded earlier. So now this is where I think it gets a bit more interesting. So here I'm setting the multi-step LR. So basically the learning rate is supposed to change after the 4th epoch and after the 8th epoch based on this gamma factor of 0.1. Now I don't know what effect this has if say I use a gamma of 0.01. So that's something to be experimented with based on whenever it is or whatever use case it is you have. For the top K accuracy, I'm setting this to 1 and 3 because by default it does a top K of 1 and 5. But since it's just 7 classes, you could find like top K of 5 and it could be doing really well because it gets the top 5 correctly. Meanwhile, it's like just flipping the whole thing upside down. And because it's 5 classes, you feel it's good enough. So I said to reduce that to top 3. Now, because I'm setting this here for the while evaluator, basically just putting this variable in here. Now, that's not necessary. I could easily just create the dictionary here explicitly. So for the sampling frames data, I'm setting the number of clips to 3 here. So let's see what the train pipeline looks like to understand the thought process behind that. Where the number of clips they have here is 1. I'm setting to 3 because I intended to take 3 samples per video. That's because I'm doing like data augmentation later on. So if I do a sample of 3, I could easily augment the 3 samples and get a larger data set compared to what I had from the start. So that's exactly what's being done here. Accessing the second operation in the pipeline, setting that to 3. And the frame interval here, the frame interval refers to the interval between the adjacent samples. So say here they have a frame interval of 32. If they sample the second frame, just as a trivial example in the video, that means the next sample is likely going to be coming from 32 frames after. But because my use case is like a much smaller video, I did not want to have, and I'm doing like 3 samples, I did not want to have a case where the samples are like spread out and they are all similar, so that's why I'm like reducing the intervals and the sampling space. Then I did that for the train and validation pipeline, so I get like consistent results. Then this part here, which is extra augmentation, I'm using the image augmentation library for that, which it supports. I could just like visit image augmentation and see what those things do. But the first operation here, it just adds random values between -40 and 40 to various pixels. Just make it change. Now this provides much more variety in the videos, especially since I'm sampling 3 videos and I want like, I don't want the videos to look all similar, so it's just an augmentation technique. Adding salt and pepper, that adds some noise to the images, or to the videos rather, and that does it per channel. Then image compression, that's the JPEG compression. Since I think the videos are about 480, 360p, I'm setting just random compression for the samples there, between like compressing 70 up to like 70% of the quality or like 99%, just in between, just to provide much more robustness to the augmentation process. So like data augmentation on its own is a completely different ball game if you know how it works, but I'm just showing here that it supports a library you could use. So even if you don't have like a big data set, you could make use of augmentation to get more variety for examples. So that's about it. I think we still have some time for this to finish running. How many epochs is it up? Okay, it's at the third one. Okay, I think we could just keep it at that. If we get to run out of time, I could just stop at whatever epoch it is that's trained up to and proceed to the remaining parts. But since we still have some time, I think a couple of minutes, we'll just do it. If there are any questions so far. Okay. I'll take the first.
So the videos, you split them already by a single action, so there's no, is there a way to split it, like to recognize that the action is finished?
Yeah, so that's based on like, do you mean doing this dynamically, so like writing a function to do that? I don't know of any technique to do that, since if you could find where the action ends, then you probably don't need the model in the first place, I guess, since it answers the question. I mean, for all of the data sets I've seen so far, they are like clipped. So say for the kinetics data set, someone is climbing a rope, so it just takes from where the person starts climbing to where they stop climbing, or it could just trim it at any point since it still implies climbing, right? So in my case, I just clipped from where the O grappling starts up to where the training, the throw ends. So I did that manually. If there's a way to do that with code, that would be awesome.
Yeah, so I'm doing a similar task, but for a slightly similar unrelated domain, which is partner dancing. So you have 2 people acting just like in Judo, but I guess it solves the problem of having to stop it, because usually you're dancing to music, so usually you know when those positions are cut. But I was wondering if there's any way to incorporate additional information. So for example, you can put accelerometers on people performing the actions and possibly use that data, or have, rather than just having a single video clip, you can have a video clip from like multiple different cameras to get different angles, because there's occlusions that happen sometimes, so possibly does that improve anything, or have you seen people try that in the field?
Actually, I think that would actually help your data sets. The main reason why I say that is, even from the videos, when I was like coming up with them, if you check YouTube for throws, you could see a single throw that was taken from like various angles. So like the throw could come from the left, and in the same compilation video, you find the same throw being executed from a video on the right. So I would like to believe that having that kind of variety from different angles helped. So if you have various cameras, it would just be a case of having your clips say the same dancing step from different angles, putting those together into a data set. That would definitely help. For the question on having like a sensor with the dancers, I think that would be like a different problem space, since now it's no longer going to be images. Now you're going to be dealing with like tabular data, since it's sensors and numbers. So that could be a different model completely. If any of the actions or what the sensor says has any influence on the actions, so you probably would need to do like some feature engineering to see if there's even any relationship in the first place between when the sensor says the hand has been raised and the leg is being raised at the same time. So that would be additional info, but I fear that it could add some noise, since except the sensor is very good and like quite explicit with what data it's collecting, then it's kind of hard to know to like link the data to the actions. So it feels like images kind of just fits that use case. Intrinsic, like just like in an intrinsic nature, if that makes any sense. Any other questions? Okay.
Yeah, I'm quite curious in regards to augmentation of videos.
Okay.
In this case of augmentation, will you be like taking the video from different angles? It's not like what you're going to include to augment the video, to augment the video.
Okay, so for augmentation, you can only augment the angles that already exist in the video. So I could just visit the link for the site, so you see what kind of augmentation techniques exist. But I don't think there's a way to augment a video to provide a different angle, since the video has been taken already. But you could flip, you could rotate if that helps. It's weird to like rotate a judo video, since nobody goes doing judo like this. So such augmentation processes probably don't make sense. So it depends. Flipping or rotating could probably help in a different use case. For context, I once worked on a project to like detect tuberculin skin induration, so like just swelling on the skin. In that case, I could rotate the pictures like whatever angle I wanted, and it still made sense. So it all depends on the domain and the use case. So you really cannot just like plug and play if you don't know what the use case is. While we wait and hope for this to go a bit faster, I could just visit the image of page to see what augmentations exists, img.org. So you have this. I think these are like basic examples, but this is an overview. Let's look into something like this. So that's like a long list of different augmentation techniques you can perform. So in this case, this is the add augmentation I did earlier. So it just adds random numbers to the pixels. It does that to all the channels, and you can decide to do that per channel. This adds noise elements wise. This adds Gaussian noise. So it all depends. Like there's a long list of augmentations you could perform, all based on your use case. This is just adding random squares. Like if that makes sense for your use case, then just use it, I guess. I've personally not found a use case for that. I mean. But that's just what, I think there are other augmentation libraries as well, but this is just my favorite. I think he uses the CPU. Can you see the question again? I think I missed it. Yes, it is in the data loader. If you check here, here, so I'm inserting it at 2 points before the end of the data loader, where the data loader looks like this. Where the pipeline rather looks like this. So I'm ensuring it happens before these final 2 steps, which are needed for the MMAction library. For the augmentation. No, I think it does it once. So like it does not happen while the model is training. It just does it at the beginning part. So it's a one-time process. Okay. I think this is the sixth rather. Just trying to see what the accuracy is like to see if I can just stop it, and it's still quite poor here. So a little bit of more patience would help. Wow, any other questions? Okay.
Is there a temporal element to the model? So is it looking at the time between the clips? Because I feel like the most value that this sort of model can give would be predicting force. But to do that, you need the acceleration, as well as obviously the mass. Because for an opponent, for example, it depends how hard the guy landed, or in boxing, to scoring, what counts more, 3 jabs or a big punch? That's where the real value comes in, measuring that sort of thing. So could this model tackle that sort of problem, or are you only looking at the clips as static?
So the models do not exactly, it could be that we could tackle that problem specifically, but as it stands, all I'm looking at is the action. So I was doing like a small check to determine if a throw is an econ or not, but the issue was like finding enough data sets of such throws. But I do believe that if you have enough data sets for that, it would actually be able to detect, since an econ would be executed in a different way. And as you said, it's like in the temporal nature, you could find this across multiple clips. For this specific model, it does the attention mechanism across time as well. So that's also accounted for. For the question about the speed, if you intend to do that, then I guess you probably will need a sensor for something like that. If you could do it from images or videos, would be an interesting question to take a look at.
Well, I thought the video might be able to remove the need for a sensor, because you should just see how fast a punch lands or how fast the throw is, because that's going to imply force, isn't it? There'll be some relationship.
Yeah, there should be. I'd imagine to detect such nuances, you'd probably need to have much more control over how the sampling works, because now you need to like understand where the frames would probably be across multiple videos. So yes, I think that's possible actually. Okay. I think this should do it. The 6th epoch says 0.75. It could be way better, but save our time. Let me just confirm that the checkpoints are there to avoid undoing all the good work. Okay, epoch 6, yep. Okay. I'm just going to stop the training process because of time. Filtered. Then this remains the same, since it's the same custom config file. I'm just going to change the epoch to, I think it's already as the 6th one. So copy path. If I need to take this out, I need to close the tab since I'm not going to do it. Okay. Then just going to find a video to do a prediction of this. Things from the validation. Okay, say that the ruler. So let's see if it gets that right. Please do. Okay, then top 5. Okay, that was wrong. This is what the user looks like. I'm just going to check another video as well. So So you see what it looks like. But the first inference is wrong. That's what these are doing looks like. So just need to check another one. Maybe we should have looked at the bit more. Let's see. Also, I just thought to mention that the video file type, we kind of worked with different video file types I've seen so far. So I've been able to work with MP4 files and WebM files as well. Okay, yeah, I got this right, the CNRD. This is what the CNRD looks like. Not sure why it's not playing the exact video. Let's just do that again. It's not playing that. Okay, is there something else? Okay, I think it's the file type for playing videos. Okay, that makes sense. So the main reason it's probably not playing videos is because Colab does not recognize WebM files, but the framework itself recognizes them. But we did get this tool right though, which is the Taigatoshi. Just going to look for like an MP4 file. So it actually plays it and we see how it works. I think this is an MP4 file. Okay, got that right, Taigatoshi. Okay. Yeah, that's the Taigatoshi. And we got that right. Is there another one we should probably check? Okay. Kochigari. Let's see. Now, if you want to run an actual test, there's a function to do like testing, so you don't have to like copy files just because I'm looking to run the model in real time. But there is a test function that you could use to get metrics. Okay, go to Granny. Let me get that right. Yeah, you got that right. And this is what the code to Granny looks like. So, yeah, that's about it. I think it works. If we had waited a bit longer, then we probably would have gotten the first one right as well. But I hope this was beneficial and we were able to learn something from it. Thank you very much. Are there any other questions? So I'll be open to answering them.
The slides going to be posted?
Yes, they are available in a certain Google Drive. We're told to post slides there, but I could post it to the Slack channel as well. There's a Slack channel if you're on it. Yeah, it's available there.
Thanks.
Thank you.
Thank you.